How's it going, everybody? Mr. Dickin here, and in this video we're going to be discussing the chain rule, which is another derivative technique that we can use to find the derivative of functions. This is going to come particularly in handy when we're dealing with composition of functions. Now, we've already talked about quotient rule, we've already talked about product rule, power rule, all of that, and those will still come into play, but now we just have another tool to add to our arsenal in the chain rule. Before we get into it a little too far, let's go ahead and remind ourselves how composition of functions work. So here I've got three different functions. I've got f of x, g of x, and h of x. If I wanted to do f of g of x, that essentially means I'm taking the g of x function and plugging it in for x to the f function. So the f function is 4 times something, and in place of that something, I'm throwing in the g of x function. All I have to do from there is distribute and simplify. If I wanted to find f of g of 2, well, first I need to figure out, working from the inside out, what is g of 2? So I'd go to my g function. G function says take something and square it, and then subtract 2. We're plugging in 2 for x. We get 2 as a result. I'll then take that result and plug that in to my f function, which says 4 times something. Well, the something I'm using here is now a 2. If I want f of g of 1, I first have to figure out what g of 1 is. So I take 1 squared and take away 2. I then take that result and throw that into the f function. F function is 4 times something. Now, if we go the other way, if we switch around our composition order, say do g of f of x, it's going to make things look a little different. Well, f of x is 4x, and I'm plugging that into the g function, which says something squared minus 2, right? The g function, g of x, was x squared minus 2. So I'm plugging in for x, I'm plugging into that the f function, which is 4x. So 4x quantity squared is 16x squared, take away 2. Here I have some more examples with composition. Now we're bringing the h function into the mix. The h function says take something and then add 1. We then take that result, put it into the g function. If we take the h function and plug that in to the g function, the h function says take something and add 1. The g function says take something, square it, and then take away 2. For this one, we'd have to do a little bit of distribution. Right, x plus 1, quantity squared. If we're comfortable with the shortcuts, we know that it's going to end up to be x squared plus 2x plus 1. But if we're not comfortable, we'd have to actually distribute that out. So x plus 1 times another x plus 1, which gives you x squared plus 1x plus 1x plus 1. And then these guys would combine to be 2x in the middle. All right. Now let's identify composition of functions as to kind of who's being the outside function and who's being the inside function. When we do this, we're going to have to first try to find where the variable x is, and that will typically tell us where our inside function is. We normally use the letter u to represent our inside function, and then f of u is going to be whatever the outside function is. And in doing so, we have this u function being plugged into the outside function. So the inside function is getting plugged into the outside function. So if I look at the first example here, I've got h of x equals 5x minus 3 quantity to the 6th power. So as I'm looking at this, I'm looking for my inner function. So I focus on the x first, and I'm noticing, okay, the inside function is going to be this little 5x minus 3 chunk, which then means the outside function is, well, what's happening to that 5x minus 3? The outside function is I'm taking whatever that input was and bringing it to the 6th power. So my outside function is something to the 6th. My inside function is, well, what was in there? That was 5x minus 3. The way we represent that quote-unquote something, or that empty parentheses, is we can just put a u there, and that u is kind of a space holder. If I take a look at number 2, I'll first find my variable, x's. Okay, and I'm seeing my x's. All right, here I've got x squared plus 3x. That's going to be my inside function. The outside function is stuff underneath a square root symbol, or a radical. So my outside function is the square root of something. That something we just refer to as u, which was our inside function. So that u is just kind of a space holder. Number 3, I first find my variable, the x, and I'm noticing, okay, that's with the 4x minus 5. That's my inside function. My outside function then is taking whatever the input is and raising it to the third power. Number 4, I find the variable x. I've got 25 minus x squared, so that is my inner function. The outside function says we take 3 times something and raise it to the 8th power. Number 5, I find my variable, which is x. That's going to tell me what my inside function is. Then I figure out what's happening to that inside function to get my outer function. Well, the outer function is take the square root of something. And again, we're using u as that something. Number 6, we find our inside function. We find our variables. Right here we have a bunch of x's flying around underneath the radical. So our u is going to be 5x squared plus 3x minus 6. Our outer function is taking the cube root of stuff. So when we get deeper and deeper into chain rule, it's going to be very important that we're able to identify kind of what our inner versus our outer functions are, so that way we can take derivatives appropriately. All right, so now let's get into the chain rule. Bum, ba, ba. Here is the chain rule. If you remember nothing else from today's video, remember this. Remember the chain rule. Chain rule says, if you have one function composed into the other, you have to first take the derivative of the outer function, leaving the inside function intact, and then multiply the derivative of the inside function. So kind of think of this as almost like an onion, right? We're peeling away layers by taking the derivative. Or a Russian nesting doll, if you're comfortable with those. So you have to get rid of the outside function first by taking its derivative. The inside function stays intact, and then multiply by the derivative of the inside function. All right. So if we take a look at this first example, I've got all the work shown out here. We'll explain piece by piece. I'm going to first find my inside function, which is 3x squared minus 6x. That's going to be my u function. I can take the derivative of that pretty easily, just simple power rule. So bring the 2 down, times 3 is 6x, because the exponent decreases by 1, minus 6. The outer function then is saying something to the 5th power. Well, I know how to do a derivative of something to the 5th power, right? I just bring down the 5 out front and then decrease that to a 4. So the derivative of something to the 5th power would be 5 times something to the 4th times the derivative of that something. Right? So 5 times something to the 4th times the derivative of that something. Well, we already know what u was. The derivative we just found gets multiplied at the end. And I'm noticing right now we forgot an exponent of 4 right there. Whoopsies. That would be our answer. We'd leave it as is. You could distribute it, but I mean, who's got the time? Who's got the time? All right, next, we're going to identify our inside and our outside functions. Our inner function, look for the variables, look for x. Our inside function is going to be 2x cubed plus 5x squared. As soon as I know my inside function, I can immediately take the derivative of it. Most of the time, that's just going to be some quick power rule. Then let's take a look at our outside function. My outside function, well, what am I doing to this 2x cubed plus 5x squared? I'm multiplying it by 5 and raising it to the 11th power. Well, I can take the derivative of that, 5 times something to the 11th, multiply that 11 down to the 5 to get a 55, decrease the exponent by 1, and then multiply by the derivative. So u gets replaced with this 2x cubed plus 5x, and that was kind of the first thing we identified, was that inside function. And then u prime, that was the derivative of the inside function, 6x squared plus 10x. So we're taking the derivative of the outer function, we leave the inside untouched, and then you multiply by the derivative of whatever that inside function was. Let's get some more examples here. Figure out what is the inner function, so find the variable. There's our inner function, negative 2x plus 3. We can get the derivative in a heartbeat. Then to take the derivative here, we'll apply power rule. So bring that negative 6 out front, decrease the exponent by 1, multiply by the derivative of the outside function. So this was u prime right there. We're typically not huge fans of negative exponents, so we move that down to the bottom of this fraction to become a positive exponent. And then we've got a negative 6 times a negative 2 to give us a positive 12. Then the last step is just swap out u for whatever our inside function rule was, negative 2x plus 3, and we're good to go. Number 4, identify your inside function, find the variable. As soon as you know that inside function, you can get its derivative very quickly. Then our outside function is 1/4 times something to the 16th. So to get the derivative, multiply the 16 to the 1/4, which is 4, decrease the exponent by 1, and then if we multiply by the derivative of whatever stuff was inside, that's multiplying by 8. So if u was 8, we'd have 4 times u to the 15th times 8, and that's where that 32 comes from. 32u to the 15th, well, u was just our inside function, so we can swap that back out with 8x plus 2. Number 5, very similar. Inside function, find the variable. 7x plus 2, or sorry, minus 2, so our derivative is 7x. When we take the derivative here, kind of skipped a step, so I'll write the in-between step. We're going to multiply the 1/2 times the 4, and then decrease that by 1. So if I were to find the derivative, y prime, that's going to be 2u to the negative 1/2, which is going to be 2 over u to the 1/2, which is going to be 2 over square root of u. You can leave it as u to the 1/2, that's totally fine. Now, when we simplify, we can multiply by u prime, because that was 7. So that's where this 4 over 2 times 7 comes from, but we could also simplify this right here, and in fact we should. That would be 14 over the square root of 7x minus 2. All right, number 6, find the variable for your inner function. That's going to be the u value. You can find the derivative very quickly using power rule. Anytime we have a radical, it will be in your best interest to think of that as an exponent of 1/2, which then means our derivative would be, using power rule, 1/2 u to the negative 1/2 power, which is really 1 over 2 times u to the 1/2 power, which is 1 over 2 times the square root of u. The more and more you do these, you'll very quickly see anytime you have the derivative of a radical, it's going to be 1/2, or 1 over 2 times the derivative, or 1 over 2 times the radical. All right, so once we have that, we'll take the derivative of our outer function, which we just found out. The inside stays untouched. Then we multiply by the derivative of the inside. So this 2x minus 2 is the derivative of the inside. That gets multiplied at the end. Now when we write this, we would probably just throw it all as one big fraction. And what this does is it allows us to see, hey, maybe I can reduce things down. And I'm noticing that, yeah, actually, you know what? I can divide a 2 out of everything. This would be an x minus 1 all over the square root of x squared minus 2x. If I divided every single term by 2. All right, home stretch, 2 more. Number 7, identify the inside function. Then find its derivative. Then we'll write the outside function as 1 over something to the third. Well, that something is just a u. Well, I'm not really a fan of having exponents in the denominator if I'm trying to do derivatives, so we'll write that as a u to the negative 3, something to the negative third power. Using power rule, multiply that out front, decrease the exponent by 1, and then multiply by the derivative of whatever that inside piece was. And we already found that was 4. So when we do that, we have negative 3 times our u function, 4x minus 3, to the negative 4th power, times 4. Negative 3 and 4 multiply to give me 12. This negative exponent gets flipped down to the denominator to become positive 4 down there. All right, and then the last one here, I'll let you just kind of pause the video to peruse over it, but it's going to be the exact same process. Identify the inside function, then take its derivative, figure out what your outer function is, take the derivative of the outside function, leave the inside intact, then multiply by derivative of the inside. That's it, that's all. If you're feeling a little shaky on this, that is to be expected. Chain rule definitely takes practice before you kind of really get comfortable with it. This was just kind of an introductory piece, but you know the drill, folks. If at any point you have any questions, do not hesitate to ask. And as always, good luck, have fun, be safe, roll tide.